Hello,
Hello, Tom.
good morning, good afternoon.
Hi, hello there. We are currently, so the Zoom is set up and we are currently waiting for everybody to be ready. Thank you for being here.
Hello. Thank you.
Good morning or good afternoon, everyone.
Hello.
Hello.
Hi, good morning.
Hello, everybody. So can you hear me or remote people? Tom, stuff? Yeah, okay, thank you. So let's start. So we are here together for the PhD Defense of Le Guillou that will present her work on distributed topological data analysis. This work is assessed by a number of people that I'm going to list, and I'm going to go through this everyone, and so you know everybody that is present here. So we have first present remotely David Kerjoli, that is Director of Research at CNRS, as been a reviewer of the work. Tom Peterka, that is Senior Scientist at Argonne National Lab in USA, that has been a reviewer as well. Isabelle Bloch, that is sitting here on my left, is professor at Sorbonne University. He's a minor. Frédéric sorry, I'm sorry for misspelling your name. Assistant professor from Clemson University, present remotely. Christophe Calvin, senior fellow at CA, that is present remotely as well. And the two PhD advisor, Pierre Fortin, professor at University of Lille, you're sitting on my right, and then just after, Julien Tierney, that is Director of Research at CNRS. You have 45 minutes to present your work, then time for questions. Thank you. The floor is yours.
Thank you for the introduction. Good afternoon and welcome to my PhD defense. My PhD was funded by the European Research Council under the project name TORI. And though I'm technically registered in Sorbonne University, I spent most of my PhD here in Cristal. And I will now talk to you about my work on distributed topological data analysis. First, let's talk about data. So what is data? Data has two sources. It can either be simulated data, that is produced with software, such as here, a simulation of the universe. Or it can be acquired data, where we have a physical quantity that is measured, such as here, the scan of this foot or an image of a microscopic image of a cell. But data itself is useless if we cannot extract information from it. That is where topological data analysis comes in. It's an ensemble of methods that will extract the structural characteristics of data sets in order to facilitate their representation and their analysis. Here, with the example, what does that mean? It means we can extract the structure of the universe and underline what is called a cosmic web. It's kind of like a web of galaxies. Here we can identify the bones of each of the toes. And in this image, we can segmentize with the image and identify each cell of the image. There are a lot of software that allow for TDA, topological data analysis computations. They are usually differentiated by two characteristics. The first one is dimension of input. It can be either low dimensional data or high dimensional point clouds. And the second is the scope of usability. That means how much of TDA is implemented in the software. It can be either one abstraction, so it's a very monotailored implementation. It can be something a little bit wider, but still somewhat narrowly defined set of methods. And then it can also be a very versatile and wide-ranging implementation. There are software that fit in each of these categories. For example, DIFA computes the persistence diagram. So it's a very mono-tailored implementation for both low dimensional data and high dimensional point clouds. We also have River, Goofy, Fat, Dionysus. All those software have practical use problems. First, they don't describe all of TDA, but they also have sometimes a limited number of input format, or they are limited to command line interface use, which motivated our use of TTK, because TTK is very versatile and wide-ranging implementation. So what is TTK, or the topology toolkit? It's a C++ library that is open source. It's quite a significant project now. It's 165,000 lines of code, over 40 contributors over the years. It's got 3 APIs, one in Python, one in VTK, and one in C++. And it can be used as a PowerView plugin. PowerView is a very well-known visualization software, and that allows TTK to harness all of the features that already exist in PowerView. But when we want to apply those algorithms on very massive data sets, there's still a problem in terms of performance, both in terms of long execution times, because even if the algorithms are polynomial on massive data sets, it still needs significant execution times. And also another problem is the massive memory footprints that massive data sets impose. And this is where parallelism comes in. So parallel computing is a certain type of computing where different things will happen at once, so they will happen in parallel. We have different types of parallelism. One is shared memory, where you have one computer, one node, and several cores on that computer. Different ways of programming that. We can use thread-based programming, where we have multiple threads that will perform computations, and all of the threads have access to the same memory. We can also do task-based programming, where the threads still do the work. However, the work itself is divided differently. It's cut into tasks that are put into the task pool, and then threads will pick out which tasks they want to perform. Both of those programming are available in OpenMP. OpenMP is a high-level standard for shared memory parallelism, and it's actually already implemented in TTK. And that allowed for a very good performance boost in terms of execution time, but that leaves us with still the bottleneck of the memory. And this is where distributed memory parallelism comes in. So the concept of distributed memory parallelism is that we have different nodes, different computers with a process on each node, and they are all interacting together in order to perform the computation. Each node doesn't have access to the memory of another node. It doesn't have direct access, at least. So we have to take extra measures for the overall algorithm to perform correctly and efficiently as well. One of the ways to implement distributed memory parallelism is through MPI, or the message passing interface, where it allows for one node to send a message to another node, but everything needs to be explicitly defined. It's quite low level, and it's one of the most popular solutions. There are other alternatives. Here are a few, like the Partition Global Address Space, or Apache Spark, or DIY. Some of the solutions are even built on top of MPI, and they try to mitigate both difficulty of use for the developer and performance. But they sacrifice a little bit of precision that we need in our application. So we'll go for MPI, but we can actually fuse those two together and do something a bit more hybrid. For example, hybrid MPI plus OpenMP, where each of the node will have multiple threads, but then there are also multiple nodes that will discuss with each other. One last architecture that I'm going to mention are GPUs. GPUs are characterized by a very high number of threads, but they don't typically scale well on TDD algorithms because TDD algorithms have characteristics that don't work very well with GPUs. Those characteristics are, they require a lot of irregular memory accesses, and they also sometimes produce little computation, so that combination of fact doesn't really scale well. But most importantly, right now, our bottleneck is the memory. And on a GPU, on one GPU card, there's not more memory than on one CPU card. So we're gonna choose the best of both worlds and go with hybrid MPI plus OpenMP programming. In order to solve the following problem, so we want to develop new topological data analysis approaches tailored to distributed memory systems, while at the same time maintaining the shared memory parallelism that is already existing. That entails a few challenges. The one is that we need to completely revisit some of those algorithms because they won't work at all in a distributed setting. And we also need to provide a seamless integration of multiple algorithms within a pipeline. A pipeline is a combination of algorithms that will compute one after the other. And because of that, and because we want a seamless integration that entails a few conditions on the output and inputs of our algorithm. To solve that problem, here are the contributions that we propose. So we provided a unified framework for distributed topological data analysis. That means first extending the core data structure of our software for a distributed memory setting. Then also designing and implementing several simple algorithms for a distributed memory setting, and also providing a low-level framework for developers. Once that first part was done, we used this framework and designed a new algorithm to parallelize a more complex abstraction called the persistence diagram. And so to compute this, we provided hybrid MPI plus third algorithms so to compute that. I will now talk about the first part of this PhD defense. So the software framework that it was detailed in this following paper. This paper was published in IEEE TVCG in 2024 and presented at this 2024 as well. Before talking about how we distributed things, let's talk about what it looked like originally on one node. And we're going to look at simplices. Simplices are elementary blocks with which we'll build the grid. Those blocks are vertices, edges, triangles, and tetrahedra. And we will use those simplices and combine them into a complex called a triangulation. It's intuitively like a big grid, and it can be either structured, where all the simplices are regular, or unstructured, where they can be irregular. And now that we have this grid, on it we will define a scalar field. The scalar field is the physical quantity of interest. For example, here, in the simulation of the universe, the scalar field is the density of dark matter. Here, it's the density of matter. And here, it's the intensity of the light through the microscope. Right, so now we have a model, and we want to distribute it. So what do? We use pair view to cut the domain into smaller blocks. We use pair view, but it could be any other software that does the distribution. And now that we have smaller block, we will add a layer of ghosts. Ghosts are simplices that are the interface of two blocks. And so they are duplicated because later on they tend to reduce the need for communication. Once we have the ghosts, we'll add 3 more information in our domain. The first one is a global identifier for all of the simplices. So all of the simplices have a unique identifier for the entire domain. Process identifier, because even though some simplices, for example, the ghost simplices, are present on more than one domain, we said that they are only owned by one. And so the process identifier is the rank of that process, the number of that process. And then the last thing that we'll do is compute a list, what we call the local adjacency graph. It's a list of the neighboring processes. For example, here, well, it's all the others because they are next to him, next to it, because those processes are privileged communication partners. All right, so now we've distributed the data. So let's look at the processing step of a pipeline. The first thing to note is that everything I've just said about the inputs is also true about the outputs, the global identifiers, etc. then what happens? The first thing we do is the preconditioning specific to the distributed setting. So that will be the computation of ghosts with Paraview, and then a series that I will not detail here, a series of steps. First, the local adjacency graph, so that's the list of neighbors. Then we instantiate the triangulation. In that step, there are things such as the generation of global identifiers. We then compute the process identifiers, and finally, some preconditioning in order to ease and speed up later on ghost data exchanges. Once that is done, we do the traditional TTK preconditioning, and then, and only then, we compute the algorithm. The goal of the preconditioning is that it speeds up the overall pipeline, because if the triangulation stays the same, the preconditioning is not recomputed. So in the pipeline, it's possible that the preconditioning is only computed once. And that really speeds up the entire pipeline. Right, so now we've looked at how a pipeline executes. Let's look at algorithms, example of algorithms, and more specifically here, how they are computed on one node for now. So the first example that we distributed was critical points. Critical points are local minima, maxima, and saddle points of the data, and they are computed by local inspection of the neighboring vertices. The second algorithm is a discrete gradient, so we compute a gradient. And again, it's performed through local inspection of the neighbors. And it's also an alternative way to compute critical points. Here, they are called critical simplices. And the gradient will pair two simplices together. That's the little red arrows. They pair simplices. Another one is the integral lines. So integral lines will pair critical points through the path of steepest slope. And then one last algorithm that is not shown on this slide that we've distributed was a smoothing operation where for each vertex, its new value is the average between its value and the value of its neighboring vertices. And that averaging step is performed more than once. So let's look now at how we've parallelized this algorithm in a distributed setting. For the critical points, there's actually very few to do because we already have access to the neighbors of all of the vertices thanks to the ghosts. So all we have to do is say not to compute critical points for ghost vertices. That is also true for the discrete gradient algorithm. And we decided to put those two algorithms in the category of not communication, because once the distribution and the preconditioning is performed, there's no communication happening during the execution of the algorithm. Then the third algorithm, is the smoothing operation. And here we need to have at least one communication at each iteration because we need to update the new values of the ghosts. We decided to put this algorithm into data independent communication category, because here we know beforehand when and for which vertices we will perform the communications. And then finally, for the last algorithm, here it's a little bit more complicated. So each process will start the computation of the integral line that starts on its domain. And then once it reaches its ghost, so another domain, it will send a message to the owner of those vertices, to the other process, for that other process to continue the computation. And this algorithm fits into the category of data-dependent communication because there's no way to know beforehand whether there will be a lot or a very few communication. You can have an instance where all the integral lines will begin and end on one domain, or go back and forth between two processes. There's no way of knowing that. Let's now look at the performance of those algorithms. So here we took data sets and we executed the algorithms on an increasing number of nodes. And the performance is represented in terms of efficiency. Intuitively, an efficiency of 100% is when by multiplying by 2 the number of nodes, we will divide by 2 the execution time. So the goal is on 100% of efficiency, even though it's in practice not reachable. And here, for those two algorithms that have no communication, we have a very, very good efficiency, as expected. For the smoothing operation, because it's a data-dependent communication algorithm, we have an extra cost for that communication that we can feel here. So we have a drop in efficiency, but once that cost is paid, we have actually very good scalability. And then for the integral lines algorithm here, we see that the efficiency really depends on the different data sets, and it somewhat drops. But if we look at the execution time, we still have a satisfying performance. Now, because that was our goal in the beginning, we computed all of our algorithm within a pipeline on a massive data set of 120 billion vertices. We computed that on 64 nodes, so that's a total of 1,536 scores. And this computation took under an hour and a half. And if we look at the execution time of each step, so each algorithm of the pipeline, we can see something that interests us. It's that the preconditioning specific to TK, so orange, dark red, and dark blue, is here and is negligible compared to the execution time of the other algorithms in light blue, and also compared to the execution time of the ghost cell generation by Parvy. So that's a very satisfying result for us. Right. Now I will talk about the computation of persistence diagrams in a distributed memory setting. Again, this entire part was described in this paper, which we submitted to IEEE TPDS, and it's currently under the second round of reviews. So first, let's talk about what is the persistence diagram. Here are two examples, and it's a topological abstraction that will extract the structure of a dataset in a very robust and concise way. That's what makes it very popular, especially for datasets that are noisy. What does it do? It will pair together critical points. But how does it pair them? Using something called the filtration. So the filtration is a sweeping from the minimum to the maximum of the dataset. And we can see that through that sweeping, topological structures, such as faults, will appear and disappear. Places where those appears or disappear are where critical points are. And so one pair of the persistence diagram is where one topological structure appeared or was born and then disappeared or died. Let's look at how that looks like on our example. So here is where the first hole appears. So we create the first pair. The first pair grows because we go up with the filtration, and then another hole appears. So we create a second pair. The second pair is finished. It stops growing at the point of the yellow critical points. The first one is still growing. We have a third hole that appeared that is filled. And finally, all the holes appeared, and we have 3 pairs. The height of one pair is called the persistence and is equal to the difference in scalar field of the critical points. And it characterizes the importance of a feature in the dataset. Features that are very important have very high persistence, and then features that are very low persistence are more likely to be noise, such as here where we can barely see that it's a pair. I've just said the persistence diagram, but in reality, we have different types of persistence diagram. In 3D, we have 3. Each will track a specific type of topological structure. So D0 will track the connected components and will pair vertices, critical vertices with edges. D1 will pair critical edges and triangles and will track poles or 1D cycles. And then D2 will pair critical edges and critical tetrahedra and track voids. We can see in the distributed settings that there's a problem. For example, here, for these two critical points that are in the same pair, they are not on the same domain. So we'll have to make those processes discuss with each other in order to correctly create a pair. The algorithm that we propose for this is the distributed discrete Morse sandwich, or DDMS. It's based on DMS, the discrete Morse sandwich, which was measured by a benchmark to be the most efficient in a shared memory parallel setting. And our structure is very, very similar to the DMS structure. However, the implementation of each step is quite significantly different. The first thing that we'll do is we'll compute the discrete gradient. It's a very costly pre-computation step. However, it allows us to detect critical simplices, and it's embarrassingly parallel. So we expect that will be very efficient, and also it's easy to parallelize. Then we will compute D0 and D2 with the following algorithm. First, we offer a new algorithm for creating a distributed graph by following the gradient. And then on that graph, we will execute a new distributed self-correcting algorithm. Then we compute D1 through a new distributed algorithm. I will now describe each of those steps that are in bold on this slide. So first, how do we create the graph? So we have the critical simplices because of the gradient. And here we start from edges, critical edges, and we want to finish on those T1 and T0, so the minimas. There are two possibilities. Either we follow the gradient and immediately reach a minima, in which case the computation is done for that one. Or we reach the border of the domain, so ghost cells, in which case we send a message to the other process for it to continue the computation. And here again, either the computation is done or we reach ghosts and we send a message again and again until all of the computation is performed. And then we can extract this graph from our computation. This graph is a little too simple. So to explain the next step, I will choose a different graph. I will use this one to explain the self-correcting algorithm. So here we have three processes, one in blue, one in orange, one in yellow. And we want to pair the S's, those are the critical edges, with the T's that are minima. The first thing that we do is each process will compute the pairing as if they are the only one. But that means that they will make mistake. For example, S1 and S3 both pair themselves to T3. That's impossible. So at that point, the processes will exchange a message. And they will communicate, say, I pair myself with T3. And so the second process will realize that it's wrong and that S3 shouldn't be paired with S1, and it will make its best guess, which is to pair itself with T2. But that's also wrong because S0 is already paired with T2. They exchange messages, and then S3 realizes the correct answer is T1, that is paired with nobody else. And then the pairing is performed for D0. Let's now look at how D1 is computed. And here, this is the original algorithm for DMS. So it's only on one node. We start at a critical triangle and we want to reach a critical edge. And we do that through something called the homologous propagation. How does that work? So first we select the edges of that triangle. So that's called the boundary. And in that boundary, we select the highest edge. That edge is linked to a triangle because of the gradient. And we will add the edges of that triangle to our boundary. And then again, we select the highest edge and over and over and over until reaching the critical edge. So this is what happens on one node. And let's look at what happens in a distributed setting. The key element that we added is the computation token. Even though at any given time, there are several propagations that are being computed. For one propagation, there is only one process at a time that will perform the propagation. And that is the one that has the computation token. And so it will perform locally the propagation until it realizes that the highest edge is on another process, at which point it will stop locally to propagate, send the computation to the other process, and the other process will continue to perform the propagation. Now, there's a problem with this algorithm. It's that if the highest edge is on a different process at each step, then we send a computation token at each step, and that's not very efficient. That requires a lot of communication. So we added an anticipation mechanism where instead of stopping as soon as the highest edge is on another process, we keep going a little bit until a fixed number of edges, and then we send the computation token. And that really reduces overall the number of communication that needs to be performed. But there's still one problem with our implementation. For now, I said computation and communication, etc. But in reality, it occurs round by round. So we do all the computation and then all the communication, etc., until everything is performed. But that means that here, during one computation round, the workload will go down because it should. But we are left with a moment where there's not enough work to fill all of the threads. So the threads stay idle and just basically wait for the next computation round. And that's not very efficient. So what we did was we added a communication thread. So it's a thread that will continuously send and receive messages. And that means that it will continuously add work to the workload of the thread, and the thread will still stay a lot less idle. We do this and we still maintain the type of rules that needs to be performed when receiving and sending messages. And that also allows us to overlap communication and computation. Let's look at the performance results for those different versions. The first thing to note is that the basic is very bad. The execution time actually increases. So that's very not good result, but simply adding the anticipation one, the anticipation mechanism really allows us to reduce the execution time on 16 nodes. That'll be 6 times faster. And then adding the communication thread allows us to still improve. Here it's on 16 nodes, about 28% faster. One thing to note is that this is the execution time for the entire BDMS algorithm. And those differences are only for the computation of D1. So when we look at the execution time of each step, seeing that here D1 is stabilized is actually a great result because it doesn't explode anymore. It doesn't kind of ruin of our overall performance. And the discrete gradient here, that is quite costly. We can see that it scales really well. And so that it's the other steps that will allow us to have an overall very good performance. We also looked at other data sets in order to see if there was a difference in efficiency. There is a little bit, but our overall result is that on 16 node, we have about 180 of speed up on average. We also compare ourselves to the original DMS, and we can see that even on one node, we are a bit faster. That is most likely because we've parallelized a bit more things. For example, we put the computation of D0 and D2 in separate tasks, so they happen at once, which DMS didn't do. And then in terms of memory, we have a much smaller memory footprint. That is because we chose to have a bit more complex data structures, but we use them for a smaller number of simplicities, so that reduces the overall footprint. We also compare ourselves to DIFA, and DIFA is the public implementation of reference for computation of persistence diagrams. And what we can see is that on one core only, for data sets that are very noisy, that have a lot to say, we are slower than DIFA. However, as the number of cores increases, we end up faster than DIFA on all datasets. And on 16 nodes, we end up on average 8 times faster than DIFA. And then, and because that was our goal in the beginning, we also executed our algorithm on a massive example for a dataset of 6 billion vertices, and this took a little under 3 minutes. And we completed this on 16 nodes, and that's a total of 512 cores. I will now conclude this PhD defense. So in summary, we provided a software framework for distributed topological data analysis pipelines. That means extending the core data structure for distributed memory setting, also modifying several simple algorithms, and we also provided an example pipeline on a massive data set. We also provided, using the software framework, we provided a new algorithm for the computation of persistence diagrams. We provided hybrid MPF cross-thread algorithms. We showed that we improved our performance compared to state-of-the-art algorithms. And in this PhD thesis, we were very keen on reproducibility. Everything I've just said is publicly available in TTK. We also provided examples to make sure that people could reuse our software. And our first paper was awarded a replicability stamp. The second, not yet because it's not published yet, but we intend on applying to one. There are still limitations and perspectives to our work. The first thing that we want to do maybe is extend the experiments of DDMS to unstructured grid. For now, we've limited ourselves to structured grids, even though in theory, it could be extended to unstructured grid. But the specificities of how an unstructured grid functions means that we'll probably need to tweak some parameters in the algorithm in order to have optimal performance, and that's not done yet. There are also many algorithms left to extend to a distributed memory setting. For the algorithm of category, no communication and data-independent communication, that most likely will be somewhat easy to do. But for algorithms that are data-dependent communications algorithms, such as DMS, that's actually potentially a research project in and of itself. We're also heavily reliant on peer review. And that's very good because we can harness a lot of its features. But for the generation of ghost cells, that can be not a problem. But we could look into generating ghost cells in a more efficient way for structured grids, because peer review does it in a way that is similar for all, and it doesn't really harness the fact that the grid is structured. There are no adaptive mesh refinement grids in TTK, and those are quite popular in applications that, for example, cosmology, that have very massive data sets. So that could be a nice thing to have. We could also leverage GPUs, even though I've just chose not to at the beginning of this PhD. Some algorithm could still benefit from using GPUs. So that could be something to look into. And then we could also extend our software to out-of-core computation. Out-of-core computations are computations that use a normal computer, such as this laptop, to perform computations that are massive, that require too much memory for that more memory that the computer can actually give. And it will write actually to disk during the computation in order to make up for this lack of memory. And some of the tricks used in out-of-core computation are similar to those used in distributed memory computations. So that could be another angle of research. Thank you for your time, and I am ready for your questions.
Thank you very much for this very efficient and concise presentation, but very clear. Let's start by giving the viewers the opportunity to ask you questions. So we start by Tom, that is you're farther away from the reviewers. So please start. Maybe if you can display the video. Tom, it's your turn.
Okay, thank you very much. Can you hear me okay? Eve, I want to thank you for a very nice presentation and a very well-written dissertation as well. It's your outline of the work and your positioning of it, and your taxonomy of the communication algorithms and so on is very nicely done. I want to commend you for that, and thank you. I'll start with the first question. If you could maybe go back a couple of slides to slide 45, just a simple question, I think, to start. You compared your DDMS with DMS over multiple nodes in both, yeah, this one, thank you, in both execution time and memory. I'm just slightly confused what it means for DMS to run on multiple nodes, given that it's a serial algorithm. I just don't understand how that works. If you could just explain that, please.
Yes, we actually didn't run DMS on multiple nodes. This is for simplicity of representation to see how different it becomes later on. But this line is actually only on 32 cores on one node. It's the same execution time.
I see. Okay, that explains it. Yeah. Okay. Maybe as long as I have the floor, maybe I'll ask one more before I turn it over to someone else. For your limitations, you mentioned that you have yet to test or to implement unstructured meshes for DDMS. And I just wanted to ask you a little bit more about that. My understanding was that in the first part of your work, getting TTK ready for MPI, that you did everything in terms of the data structure to be able to distribute unstructured meshes, triangles, and tetrahedra. And one would think, probably naively, that, well, that should allow you to simply now run DDMS unstructured as well as structured, but clearly that's not the case. But I wonder if you could just say a little bit more about what is still missing or in order to do unstructured DDMS.
Yeah. So it actually should run on unstructured grids. It's simply that it's most likely that the benchmarks would yield somewhat different performance results, most likely because for the same number of vertices, unstructured grids requires a lot more memory. So we can't just, I can't just run the exact same benchmark on unstructured grids. So I would have to change the size of the grids to have something that will be smaller, but then it will be less compute intensive for the same amount of memory. And so we believe that it's most likely that we'll need to change some of the parameters. For example, make the communication threads more reactive, so have it send message more often and things like that. But in theory, it should work right away. It's just that it was significant enough for us to say, okay, we stop here now that it works on structured grids. And we think it's a second leg of work.
Okay. Yeah, I appreciate that. That makes perfect sense. Thank you again so much. And I'll let someone else take a turn.
Thank you very much, Tom, for your questions. Second reviewer, David, please.
Yep. Further, thank you very much, Eve, for the presentation of the manuscript. I will continue with Tom's message that everything was very fine and very easy to read to me, for even if I'm not very specialist to parallel programming. I thank you for the presentation that nicely complement the manuscript with the illustrations and all that stuff around the context of your work. I would also have a few questions on. Let me start with Tom's question, because I was also wondering why the DDMS could not apply to more general settings like complex simplicities, simplicial complexes, sorry. But you already replied to that. Is that only a limitation in memory usage, or are there something that I may have missed when you would like to handle simplicial complexes?
So the grid, the unstructured grid actually already exists in CTK, and so it technically already works. It's just that because the unstructured grid require more memory, the setting of the experiment, the setting of the benchmark will be different. and yeah, because of the memory. But it also it should work the exact same. There should be no difference other than actually the context in a way of the experiments.
I see. It's something, yeah, maybe also for the first part of your contributions related on the generic design of TDA algorithm using your MPI plus TTK framework. In the benchmark that you have mostly implicit regular domains. And I was just wondering if you have experimented a bit on more generic simplicial complexes. Does that, would that impact the way that you evaluate the results? Are there, or just because there's no benchmark on very generic simplicial complexes that you have played with?
We have something that works. We didn't, for example, the distributed pipeline we did only on regular grids, mostly because that's what our application case mostly are. But it works on others. For algorithms such as critical points and discrete gradients, the performance should be somewhat almost exactly the same. The only difference is we won't be able to execute on benchmark that have this side, because here I chose the side of the grids by making them the biggest I could on one node. So in an unstructured grid, that biggest will be smaller. But there's no real well, the algorithm, not algorithm, the API with the triangulation for unstructured grid are different from structured, because in unstructured, we have to know the things such as global identifiers or process identifiers, whereas in structured grid, we can implicitly compute them, knowing where one vertex is. We can deduce where it is in the global domain.
Yeah,
that's not true in an unstructured grid. So instead of having this extra cost of computing, we'll have an extra cost of looking into the memory. And so that's where the main difference will be in terms of execution.
Okay, I see. And in the targeted areas that you have played with, there's no such data sets, I would say, or it's less conventional.
In our applications, yes, but it does happen, and that's why it's also implemented.
Okay, thank you. I would have a more technical question about the DDMS algorithm and the homologous propagation, because I wasn't sure that if that is a problem or not. When you do the propagation, do you need to make sure that in dimension 2, for instance, the propagation is homomorphic to a disk or not, or it's not something that you would like to enforce when you performing the propagation? Probably go back to the slides where you have this homologous propagation illustration.
So actually in 2D, it's done a little bit differently. We don't actually have a propagation. So if I go back to the slide of how everything is structured. So I've had D0 and D2 and D1 for simplicity. But in a 2D computation, we'll use the algorithm that now I've named D2 for D1. Basically, D0 will compute ages and mimas. And then
Mhm.
D2 will compute maximas and saddles. And so in 2D, you have maxima and saddle and minimum and saddle, but no D1 computation. Well, no algorithm of that I've named the computation of D1. So
Yeah, but
that
even
is-
in dimension three, yeah, no, even in dimension three, when you had this homologous
Okay.
propagation, you are dealing with the boundary of the region that you are being during the propagation. Is that a problem if the boundary is not connected, a single unique connected component of simplices? Let's
well,
say if you have a kind of a torus in dimension three, when you do the propagation and you end up with multiple connected components of the interface.
I'm not sure I
Yeah, maybe that's something that may not
question.
happen when you do the propagation. Yeah, sorry about that. Okay, yeah, probably a last question to you. In the preview settings that you have, there is also the notion of interactivity and as you also mentioned, the fact that you will probably run multiple times the same pipeline with different parameters. So for now, the preconditioning is run every time you change a parameter. Is that correct?
Every time there is a change to the triangulation itself. And
Okay.
what
I see.
would you mean by parameters?
Yeah, I mean, if the data slightly change, for sure you would have to. No,
Yes.
the structure is the same for sure. Only the data, so we have to reprocess to rerun the pipeline once again.
If for example it's just the scalar field that changes, but the structure is the same, we rerun the pipeline, but the preconditioning part doesn't need to be rerun.
Okay, I see. But this is factorized somehow.
Yeah, exactly.
And for the bottleneck that you have in the pipeline, that is mostly, I mean, you mentioned that also in the limitation that the construction of the ghosts using ParView is very costly in your framework because of the robustness of the computation involved in ParView, or what's the main
Yes.
reason of that?
So I think the choice of the developers of Purview was to have one algorithm that will fit all of their grids. I think probably because of being able to maintain this, they have a lot of different grids. And so they took kind of like the worst case scenario, which is unstructured grids, where you have to perform everything and really communicate everything. You can't deduce anything like you would in a structured grid. And that makes it very costly, especially in the case where you have structured grids, because for unstructured grids, they are doing exactly what they need to. So my remark was towards structured grids where some execution time could be gained by leveraging what we know of structured grids.
Okay, makes sense. Thank you very much again for the presentation of the manuscript. We appreciate it.
Thank you very much. Federico, your turn for a question. Thanks.
Sounds great. Thank you. And thank you, Eve, for a beautiful presentation and very enjoyable to read dissertation manuscript. I definitely second all the rest of the committee. I have a mix up of questions. Some are low level and some are gonna be a little bit broad. I will start maybe with the one that are mostly driven by my own ignorance. And so the first one, very low level. It's the ghost simplices in ParaView, the one that ParaView defines as ghost simplices. Is it correct if I think of them as being always the top simplices or the top cells of a structure, like they're always gonna be tetrahedra or voxel and nothing in between?
ParaView, yes, I said simplices, but ParaView doesn't actually look at simplices. The ghost will only be cubical simplices, so cubes, and the vertices. But for TTK, there's a whole framework that allows to cut those cubes into tetrahedra. And to do it on Ghost is the exact same as doing it on other simplices.
Wonderful, wonderful, thank you. And another like very low level question, like in one of the slides at the beginning, I think it was slide 17, when you were showing the pipeline that combines like the distributed part with the old-fashioned single node part. You used two terms there, like one was, I believe, triangulation instantiation, and the other one was triangulation computation, maybe. I think I believe what is the second one, I suppose, is what TTK currently does in a single node operation, so the computation of the topological relationship in the triangulation. But what is triangulation instantiation? Like, I missed that part.
It's elements of the triangulation that are specific to distributed pipeline, such as the global identifiers that need to be computed at some point. So they are computed in this particular steps. Also, each process will identify, compute some information, such as their ranks, the number of process overall, and things like that.
Got it. Got it. Thank you. So kind of like creating the global index, the global names for all the elements.
Yes, something like that.
And starting connecting them. Got it. Thank you. So moving to more like broad question. One thing that I kept thinking about while I was both reading the document and while you were presenting was the interplay between the efficiency of a distributed approach and how we distribute the information. So how we split the mesh in chunks and we take it around like across our nodes. And I think like you said a little bit about that before in one of the previous questions. I think what was one of David's question, you said like your approach, at least like for the results that we have seen here, was to cut in pieces that were as big as you could, as long as they were fitting in each single node of your cluster. I just want to ask you more about that aspect. Like, how much have you played around with different granularity for the subdivision of the grid, for example, or how much have you tested the pipeline when you use a different subdivision?
I actually didn't quite play with cutting up the grid. I use the distribution by ParaView and kept that. What I did look into was how much processes and how much thread we should use. For example, doing something that is pure MPS processes and no threads at all. Because that's kind of our response to cutting it in different divisions. Because so the advantage, no, the goal of looking into how data is partitioned would be to find the most efficient way, to find the way where the algorithms will then later on compute the fastest. And usually one of the reasons why the algorithms lack efficiency is that there's a workload imbalance. And so you could potentially maybe find a partition that is more efficient than the one we chose by default. However, the only way to do that is to actually look into the data, because that will be data field dependent. So that asks you extra computations. And then once you do know the new partition, you have to redistribute the data. And within pipelines that can be potentially 10 algorithms long, that's that can ask even more additional time, because then you're going to want to do that at every algorithm, and you're going to change the partitioning at every algorithm. So that's a lot of additional time, might not be worth it. So our answer to the workload imbalance is the MPI plus thread computation, because then there's dynamic load balancing that is possible on one node. If you use as many threads as possible on one node. And so then the need for a more balanced overall domain is less important.
It makes a lot of sense. Thank you. And I still want to stay on this point for another question. It's more a curiosity, but I have still about this hypothesis of having different type of subdivision. Have you ever felt that like different type of algorithms, like you presented that taxonomy? Now I don't remember exactly the name, kind of like no data, no data
communication. Yeah.
That's right. Have you ever felt that these three type of algorithms, especially when you have them one after the other in a pipeline, they would require a slightly different subdivision, or at least like they would be I agree that, you know, overall you keep the subdivision static and it will probably be best just because you don't create overheads in moving the subdivision around. But, you know, in an ideal world where changing the subdivision will cost you nothing, have you ever felt that different type of algorithm within this taxonomy would require a different type of subdivision to work at their best?
It's not necessarily a taxonomy based different. I would say it's a case by case type of decision. For example, integral lines, the computation is actually a lot shorter when you have a lot of noise, because the integral line will end very quickly because it reaches very quickly a critical point that ends it. Whereas on the other side, for DDMS, having a lot of noise means a lot of pairs, so it means a lot of work. And those are in the same category of data-dependent communication. So I think it's very algorithm dependent, the type of maybe characteristic of the data that makes it go faster or slower.
Wonderful. Makes a lot of sense. Thank you. The very last question is still like broad and is more about the future works. Now I know that you listed a lot of open challenges, as I think like every like good PhD thesis should be able to identify as like we solved something, but we just created more problems now, or we found out about more problems now. I want to add more, or just pick your brain on if you think that's a problem or not, which is about like the rendering part. So I often feel that, you know, we are kind of improving the amount of data upon which we can compute things, included topological information. How was for you the experience of trying to render those new information computed on very large data?
Actually, using pair view makes it very, well, makes it mostly simple. Of course, we are in a HPC setting, so there are a million pieces moving at once. You still just executing the distributed pipeline, for example, was not something that was just simple, but it was doable with the necessary steps. And rendering itself, I didn't have to do at all. I just completely relied on pair view and on VTK. Yeah.
if I can be more specific, or just like, you know, how do you remember being the rendering time for even for some of the figures that I've seen in your document? Like, it was always something that you were able to produce, like once the computation was done, it was something that you were able to produce like interactively in real time, or also the rendering part was something that you had to do through scripts, and so kind of like in as a sort of post-processing of your data.
Mm-hmm. The rendering for massive datasets, I did on supercomputers. So I would execute like one big script, and it was all at once, so all the computation, and then the rendering was performed immediately. I didn't do anything interactively, but I think that's also because the goal of my PhD is then actually to use the things I produce, but to produce them. So having something that's more interactive is probably better suited for the people who will use the data, but that's also technically possible with peer review to have something that's interactive. My experience of it was, I would say, quite good, especially the most recent versions of peer review and recent versions of the softwares.
Sounds great. Thank you so much. That was my last question. Thank you, Eve. I really appreciate all the answers.
Thank you very much for your questions. Christophe, you have a question? Go ahead, please.
Yeah. Thank you. First of all, thank you for your presentation and also your manuscript. Congratulations for all the work you have done. Huge work covering a large spectrum of interest and many different things to understand and to master in order to have all these results. So congratulations for all that. I have some question. First of all, about I think it was on slide 16, but perhaps you don't have to reshow this slide. Just to understand why. No, it was 21. Just to understand why you have to pay one time the communication cost when your first execution point was on 32 cores, if I remember well, and the second point was on 64. So I think you have two different nodes. So this is the first time you have to pay the communication cost, and after that the curve is flat. So why we have to pay only one time the communication cost?
So you're referring to this?
Yeah, this one. So it was 24 and 48, sorry. But okay, you go from one node to two nodes, so I understand that you have to pay the communication cost there. But when you increase the number of nodes, you don't pay anymore the communication cost.
It's the communication cost is paid, but it's hidden in the speed up of the overall algorithm because we execute on more than one node. So on 4 nodes, we execute the whole on 4 nodes. So we'll pay the same kind of communication cost, but the computation performed by each node will be reduced. So overall, it's stable.
Okay, so you don't have an increasing of the communication cost when you increase the number of nodes, but so this is exactly the same cost, but since the computational cost decrease, it masks somewhere the communication cost. Okay.
Exactly.
Okay, and if you have to something also I don't really understand, if you have many different analyses to do, so many pipelines to chain, can we hide or can we pay one time this data distribution, the computation of cells and all the discretization or the construction of the tetrahedra or unstructured grids or structured grids? So I don't understand exactly if it depends on the data analysis you want or the pipeline you want to achieve, or you can run many different analyses using exactly the same discretization.
So one pipeline can yield different analysis. You can, in one pipeline, compute the persistence diagram and then some smoothing, etc., etc. So I would say yes, you can have it be computed once and then basically have kind of your pipeline that forks and then multiple analysis at once. You could do that. You just have to have the forethought of writing the pipeline so that it produces different things. But yes, you could very much do that.
Okay, so it could be also interesting because since in your distributed memory environments, since if you have already paid the initial cost of setting up all the configuration, then you can chain different pipeline, and it could be much more efficient if you chain the different pipelines in the same environment, since you have already computing everything. Okay.
Yes.
Another question. So I'm not specialist of this kind of domain, but I'm much more used from classical numerical simulation, and we use structure and structure grid meshes and so on. And I wonder why, if you have investigated the possibility to use classical mesh partitioner like Metis or Parametis or something like that, because it seems you rely on tools provided by ParaView. But perhaps it could be interesting also to investigate the possibility to use mesh partitioners, classical mesh partitioners. We use classically used in numerical simulation, and perhaps it could be also interesting to investigate these kind of tools.
So I did not look into them at all. I think the choice of using the ParaView mesh partitioner was that TTK is mostly used with ParaView anyway, and ParaView has quite an extensive knowledge and a lot of features specifically for parallel computation, specifically for HPC. So that was our first choice, but I mean, it could be something to look into as well, different mesh partitionings.
Yeah, I think it could be interesting because also you mentioned in your limitation and perspectives that you rely essentially on ParaView, so perhaps it could be an alternative to use these kind of tools in order to see if there are some advantages or not compared to the tools furnished by ParaView.
Maybe. The thing is also we use ParaView. Well, we use VTK, which is a library ParaView is programmed with to produce the images and the structures that we output in TTK. So completely getting rid of ParaView would be a somewhat significant change. But at least using different mesh could be something to look into this.
And my last question, and see, excellent transition with your personal answer. In the introduction, you mentioned topological data analysis, and my guess that is quite general, so that you apply all these algorithms and pipelines only on images. Do you think, or it's a naive question, all these topological data analysis can be applied to other data like I don't know, signals, text, or something like that, or it's only dedicated to images?
So it's not just images, it's images and high dimensional point clouds. TDK specifically only works on 2D and 3D images, but other TDA software can take in high dimensional point clouds. So if there's a way to turn any data into those high dimensional point clouds, I would say yes. I don't see how you could turn a text into that. You'd probably leave some information out.
But somewhere, if you can represent data into graphs, I think you can perhaps you can use this kind the same kind of algorithms.
Sorry?
If you can represent the data into graphs and graph dependencies between nodes and something like that, I think many of the algorithms used for images analysis can be used also.
Maybe. the things it studies holes. Well, TDA is a study of holes and handles and voids and things like that. I'm not sure how within a graph that would translate. But it's a possibility as well.
Okay. Thank you very much.
Thank you. Let's now move to the in the room persons and the jury. So please, Isabelle.
Well, thank you for the presentation. It was very clear and precise, and so thank you also for inviting me to this committee. I was already in your thesis committee, and your presentation have been always very clear and precise. But I think you have done a step more with more maturity, and you could take a step back to have the big picture, and it's very nice to see this progression. So congratulations. And so I don't have many questions. Several have been asked, so sorry if I'm asking with some overlap with other questions. Something so the manuscript was very clear as well, and I appreciated also that you spent time to make your algorithm reproducible and in open source, etc. And my first question would be, do you know if you already have users of your methods and algorithm of what you have been?
So of the first paper, yes. We have people asking us how through the TTK mailing list and on GitHub, people who were already considering using TTK and now they want to use it in a distributed setting. For DDMS, not yet, because it's probably too recent. Though I did do a presentation at the Parview User Days, and people were interested in at least the massive aspect of.
And do you know for which type of applications, which type of data?
Yes, so it was
just a matter of curiosity.
Somebody who wanted to do the analysis of meteorological simulations and trying to track features of that simulation, namely the eye of storms and the center of storms, how they move and when they appear and things like that. And so persistence is a good indicator because simply looking at the critical points is just too much data, but also simply looking at the highest also would make smaller ice disappear in the storm. So they were interested in using persistence diagrams. But then again, on massive data sets, it's still massive, so it still requires quite a lot of expertise.
Thank you. Then I had some question about what you mentioned as limitation of perspectives. And one of them is about adaptive mesh refinement. And actually, in 3D imaging, that's for massive data. It's might be useful to work at different resolutions or to focus progressively on a specific part, etc. And I understand that this raises problems from a parallelism point of view, but from a topological point of view, this may raise problems as well, no?
Yes, that's why TK is not implemented at all for now for AMR grids, because checking who is the neighbor, if it's at a different scale, that would create problems. So it's not something that would be just easy to do, and it would require.
And even the critical points could change.
Yes, they could also change locality, or if they're depending on where in the hierarchy of grid, hierarchy of vertices in AMR, they could change. So that could be, yes, the results would definitely change depending on the type of AMR grid.
And maybe another question. So you mentioned also in the perspective, I think that you would like to develop your own algorithm to handle several types of triangulations. But then how do you see that in with your constraint on versatility generalizability, etc. So
I'm
it seems that
not sure what it is you're referring to.
that's something you mentioned for the, I think for the preconditioning.
For ghost cells,
Yes. You say that designing your own algorithm would be a better way to handle different types of triangulations.
Mhm.
But then it's no more general. So
yes.
how do you see that? Can you
So
comment?
probably for unstructured grid, I would keep the purview implementation because it works already really well, and maybe only have something that is our own for the structured triangulation. So that would leave only one to maintain, because in TTK there are only two big types of triangulation: unstructured and structured. So that would still be a limited number of things to maintain. We wouldn't have the problem that Purview had of having an enormous amount of format. And the thing is, the structured is actually a lot simpler to implement if we have something that is specific to structured, because those are just rectangles and squares. So one can easily describe the entire domain simply by having the length, for example, of each and the starting point and things like that. And those are things that are already used in Purview to have very simplified ways to represent structured grids. They're just not harnessed specifically for ghost cell generation. And here, generating a layer of ghost cells would be, at least conceptually, somewhat easy, just having one more cube everywhere. I actually also implemented, because TTK is also capable of doing periodic grids for structured grids. And I implemented ghost cells for specifically those periodic grids that are structured. And that was conceptually simple. So it took quite a bit of time, because it took quite a bit of time to understand how Purview worked and everything. But conceptually, the algorithm itself was quite simple because everything is very structured and very predictable.
Thank you. So maybe I will stop here. Okay, no,
Thank you very much. I'll ask one short question. Such many of them. So you're working with very irregular algorithms. You mentioned that most of them, so they're very hard to parallelize. And as you said, you relies on BTK domain partitioning algorithms, that I guess is regular. I mean, I don't know if it's regular, but do you think there would be a benefits of trying to adjust the domain decompositions by being able to kind of anticipate the workload associated by each subdomain and making them smaller or bigger, and so partitioning maybe once and then repartitioning them? Did you think about? I'm going into the direction of trying to figure out some kind of load balancing strategies. Did you think about it? Do you have some ideas, or maybe it's just
we thought about it? Yeah, because that's one of the problem of efficiency in TDA. If everything happens on one process, the way we cut it, well, it will be only on that process that the computation is done, and it's not very parallelized. The way Purview does it is that it tries to, even on unstructured grids, it tries to have a somewhat the same number of simplices on all of the processes. It tries as much as possible to have the number of processes that to be somewhat balanced. Now, for us, that doesn't necessarily mean that the workload is balanced. But the problem here is one that would change for all algorithms, most likely, what the optimized partitioning is. So we can't do it once and then have it everything and have it reuse it. And then second, that would require some additional computation in order to predict it. That requires to look into the data, even if we know, oh, this is integral lines, therefore this is how we can detect if there's going to be a lot of work or not. This still requires some computation, so that's costly. And then redistributed the data is costly again. And doing that for every algorithm is costly again. So that might not be worth the effort. And another thing is that a lot of the TDA computations happen on simulation software. And those in a massive data set, those are already distributed on several like files or nodes or things like that. And there are analysis called in situ, where basically the analysis is plugged in as the software computes the simulation. And in that case, reorganizing the data is not possible. Well, you'd have to completely copy it, and that's defeating the purpose of in situ computations. So we chose to stick with the pair-view partitioning because in practice, it's very practical, and it's not the worst partitioning in terms of our performance, and finding the best might not be worth it.
You just mentioned in situ analysis. I think it's not something you cover in your manuscript, but can you tell us a little bit more? Maybe I missed it.
No, maybe I didn't.
So can you tell us a little bit more if you actually like deploy your algorithms onto in situ situations where indeed, I mean, you inherit from the data partitioning that is done in the simulation, so you have to work with it, but that was like just, yeah, well, how far you went with the experimenting with in this kind of in situ context?
So I didn't use any in situ applications. However, it is possible with pair-view to perform analysis with in situ. There's a plugin called Catalyst, whose goal it is to allow for that. So we did keep that in mind in order to when we designed our solutions. And then one practical, it was not quite in situ, but just opening a file for the massive pipeline, opening the file and then saving it into pair-view file system. It was already cut into smaller files. And I could see that just simply saying, okay, now it's 8 processes, I want it on 16, that would take like 15, 20 minutes. It's simply the step of just opening into the RAM and then moving the data around. So I could see in a very practical way that maybe it's not worth it for massive data sets such as this that have like 900 gigas of memory.
Yeah, thank you very much. So now time for the advisors. If you have some remaining questions or comments, you maybe want to start.
Yeah, so no question, but I would like to first warmly congratulate you for all the work that you've done during your PhD thesis. Your presentation was really high level, but and so in fact you had most of the technical and algorithmic difficulties, most of the detailed formalism that made your work really difficult in practice. You also spend a lot of time developing some useful features in TTK for distributing memory parallelism. So for example, like you mentioned the periodic grid, and you did not present this in detail, but you spent some time on it, and it's worth mentioning. So regarding your contribution on DDMS also, I would like to emphasize that that beforehand, no one knew which was the best strategy to use. And then you propose your own, you design your own distributed algorithm. Then you propose your own improvement. And in the end, the final result that you get show that you've done the right choices and these were really relevant. So in the end, I think that you have acquired a really expertise in both HPC and TDA, and real scientific autonomy. And I wish you all the best for your career.
Yes, so I don't have any questions either. I agree with what he said as usual, so I'll try to say something different. I'll start by saying that it was a real pleasure to work with you for the last 4 years now. It's been great, like Isabel said, to witness your progression through the PhD and to see the development of your skills. And that was concluded in a very nice manner by this awesome presentation that you gave today. So that was great. At a personal level, I was impressed by many things like Pierre mentioned, but I was impressed by your strength of character. And this is a compliment, don't take me wrong. Your work capacity, and most of all, your determination. And also on top of your technical contributions to the TTK team, you contributed a great team spirit at a human level, and many of us appreciated that. So thank you for that, and you will be missed. But that is all. Thank you very much.
So now we will take a moment for the deliberation of the jury. So please, we will stay here in that room. So please leave the room for a moment.